Hello, I'm Daniel Gordon from the University of Edinburgh, and in this presentation I'm going to give you a brief overview of our work on a human-in-the-loop optimization of exoskeleton assistance via online simulation of metabolic cost. Exoskeletons and prosthetic limbs are often designed with the intent to augment or assist human locomotion. For devices like these, a common measure of effectiveness is the reduction of metabolic cost offered by the device, which quantifies how much it improves the energy efficiency of gait, if at all. There are a number of open parameters that make it challenging to design exoskeleton controllers that consistently achieve significant reductions in metabolic cost. For instance, the ideal control strategies can vary based on the physical dimensions of the wearer, as well as with age, the presence of any gait pathologies, or even differences in underlying walking styles. As a result, generic controllers are often suboptimal when considered on the level of individual subjects. Recently, human-in-the-loop optimization has emerged as a framework which is highly successful in producing exoskeleton control systems which are metabolically effective. This approach uses colorimetric data collected directly from a subject in the loop as input to a gradient-free optimizer, so as to optimize some aspect of a wearable robotic device, such as a parameterized control scheme. Despite the general success of this approach, there's a clear drawback, namely the significant time investment required, which is as a result of the low resolution and noisy nature of colorimetry measurements. Long data collection protocols can induce subject fatigue, which can require human-in-the-loop optimization protocols to be run over multiple days, or, in the worst case, invalidate optimization results due to underlying changes in muscle physiology. Also, as a result of time constraints, human-in-the-loop optimization protocols are typically limited to relatively low-dimensional control parameterizations. To address this issue, we implemented a framework which utilizes model-based approaches to simulate metabolic rate computationally, thus removing the need for lengthy measurement times of colorimetry. To achieve this, we use personalized musculoskeletal models to represent human exoskeleton systems and simulate metabolic rate from real-time motion capture data. Our framework is driven by an off-the-shelf implementation of Bayesian optimization. Since simulated metabolic rate requires less time investment to compute than the experimental equivalent, we're able to explore a more complex four-dimensional parameterization of a hip flexion extension exoskeleton controller. We designed an experiment whereby our human-in-the-loop optimization framework was used to optimize the control of a hip exoskeleton. Our experiment consisted of two phases. In the first phase, subject-specific exoskeleton control parameters were identified for each subject. Then, in the verification phase, we tested transparent mode walking, our optimized controller, and two off-the-shelf controllers using a ground truth measurement of metabolic cost via a colorimetry device. In addition, we collected feedback directly from participants on the effectiveness and the comfort of each of the tested control modes. The results of our experiments indicated that the optimized control schemes resulting from our framework were preferred by subjects both in terms of comfort and perceived assistance. In addition, our control scheme outperformed the off-the-shelf control schemes at reducing metabolic cost and was more time efficient than comparative human-in-the-loop optimization frameworks, which are purely data-driven. Thank you for listening.